Okay, welcome everyone. This is our final week, last set of lectures. Forgive me, it's cold in the office, so I'm staying a little bit bundled up here. So our last set of material is from Chapter 14. We're talking about duopoly and oligopoly, which is just a small number of firms, as opposed to the monopoly situation with just one firm. So our lectures will, I believe, come in 5 parts this week. I'll start with Cournot duopoly, kind of the generic setup of it. Then we'll do a symmetric example of Cournot competition, and then have a asymmetric example. Then we'll expand it from just 2 firms to just 3 firms and compare how the outcomes differ from those early examples. And then the final part will be on Stackelberg competition, which is just an extension of the Cournot model, essentially allowing sequential game between the firms competing with one another. We will omit entirely the last section of Chapter 14, which is monopolistic competition, and the only thing you need to know about the Bertrand model, which is the second to last part of the chapter, is that it is similar to Cournot in that you have a small number of firms competing with one another, but the Bertrand model assumes that they're competing by choosing prices, and the assumption underlying that is that if my price is lower than my competitors that I choose, then I will get all of the market demand at that price. My competitors will get none. And if my price is the same as my competitors, then we split the market demand at that price evenly, which creates the very unrealistic outcome of changing my price by 1 cent can cause an infinite increase in percentage terms in my quantity demanded, which departs dramatically from reality, right? All of the simplifying assumptions that we use in our models necessarily lead to some departure from reality, but that one is sort of too big to bear, and so the model is not particularly useful, and we will omit that from our coverage in this class. All right, so where have we come to so far in this term, right? Basically, with firm theory, right, we've got this idea of market demand, which essentially captures the law of demand, which is not a natural law of the universe, but an easily accepted law of economics, right? That if you decrease the price, quantity demanded will increase, right? Which fits perfectly with our concept of utility maximization and non-satiation of preferences. Right, so then we frame the firm theory side of this by thinking so far of 2 different extremes, right? Perfect competition down here, where there are an infinite number of firms, or effectively infinite, just gobs and gobs of firms, so many that it's hard to count, right? And if that were true, then the law of demand basically doesn't mean a lot, right? But for individual firm decisions, they compose such a small portion of the overall supply in a market that their choice of quantity has no effect on the price, or no meaningful effect on the price. Therefore, they take the price as given, maximize their profits, and the result that we are favorable towards, right, is efficient outcomes, where there are no kind of mutually beneficial exchanges remaining that could be made. We exhaust all of those opportunities, assuming, of course, that that certain other assumptions of perfect competition are also satisfied. At the other end of the spectrum is our extreme version of market power, right, where there is just one firm. And what we found was that if there's just one firm in the market, then they should recognize that in order to sell more, they have to reduce the price that they charge on all of their output, which means that marginal revenue falls more quickly than that demand curve, and essentially means that the monopolist restricts output in order to maximize their own profits, and the result of that is deadweight loss, right? Which are in terms of this framework, right? Units of output that could be produced and sold at a net benefit, and yet they are not because of the losses in revenue that the firm would have to incur by reducing its price. So each of those are interesting cases, right? But they are the extremes at the ends of this spectrum that are not particularly relevant to the vast majority of actual market settings, right? So we're going to start thinking now about this interior section of that continuum there, and in particular, this side down here, where we have few firms but more than one, right? So the Cournot model we'll start with is just the duopoly setting. So we'll, again, keep it as simple as possible. Let's just make it two firms. So if I have two firms in this market and they are deciding on their quantities, right? We note that that the price at which I can sell my output is going to be dependent upon the quantity that I choose, but not just the quantity that I choose, but the quantity that my competitor chooses as well, right? Because at that total quantity will determine the market price that I can that we can sell all of our goods at. And why that kind of makes sense is, think about it, if my competitor takes that price and I try to charge a higher price because my quantity is back here, my competitor, well, there may not be the discontinuous jump that the Bertrand model assumes, where everyone would go to my competitor before coming to me. People will tend to go to the one with the lower price among us, so they will be able to sell all of their quantity, most likely, and I will be the one with excess supply because I tried to charge a higher price. So the price at which we can both sell all of our goods will be dependent upon the combination of my output and their output, right? Which, hopefully, like going on here, right, is that strategic game setting that we already set up last week with game theory, right? Here, now we have two players in the duopoly setting. We have firm one, oops, and firm two, right? And their strategies are the quantity that they would choose to produce. Choose their own QI, where I is equal to 1 or 2 for firm 1 and firm 2. And then their profits are going to be dependent, not only, their payoff is profits, right? And that's going to be dependent not only on their own output Q1 or Q2, but that of their competitor as well, right? So for firm 1, pi 1 is a function of their own output Q1, but also their competitor's output, and vice versa. All right, so we have a very, well, at least a fairly straightforward game setting, right? Where we have two players. They each make a choice of how much output to supply, and their payoffs are going to be dependent upon each other's choices and the market structure, or the actual demand curve that sets the price, and their own cost functions. Right, so we'll pause there for a moment so I can reset the board. Okay, so here we go. What are our players trying to do in this setting, right? Let's think about maximizing profit for just one of the two firms in this duopoly setting. So firm one wants to maximize their profit, which we know is going to be a function of their own quantity and the quantity of their competitor, right? Because profit is price times quantity minus total costs. So we're going to have P as a function of total quantity Q, right, times the little q for firm one minus their total costs dependent upon their own quantity Q. All right, so we have a couple of underlying relationships that we need to know something about. All right, so first of all, we have some sort of cost function. We'll leave that generic for now. But we'll give a generic linear function for demand, right, as A minus B times big Q. And we know that big Q is equal to Q1 plus Q2, right? It's just the sum of supply from the two firms. Therefore, when the firm wants to maximize this, they're going to do the exact same thing, right? In order to maximize their objective function, we're doing the same thing as a monopolist. The difference is that this big Q is not exactly what they're choosing. They're choosing a portion of it, right? So what I need to know is that dP of Q, d little q, right, is going to be by the implicit function rule, right? By the chain rule, really. However, this is very straightforward when you think about it, right? Because the derivative of big Q with respect to little q, regardless of which one I'm taking a derivative with respect to, is just equal to 1. So this product is just equal to the derivative of P of Q with respect to big Q, or P prime of Q, right? Which with our linear function that we have here is just equal to negative B. If you doubt, right, take your derivative of P of Q with respect to big Q and you'll get negative B. Then plug in that big Q is equal to Q1 plus Q2. So you'll have A minus BQ1 minus BQ2 and take a derivative with respect to little q1 and you'll get negative B again. All right, so now the first order condition to maximize this function, right, is just going to be the derivative with respect to q1 set equal to 0. And so that is going to be this is negative B. This is A minus BQ. So we have add my C prime of Q to the other side, and I've got minus BQ1 and minus BQ here with our A. This form is our marginal revenue equal to marginal cost, right? And now I can let big Q equal Q1 plus Q2 to simplify this further to so with this generic form, that is as far in as I can get on a kind of simplified version of marginal revenue equal to marginal cost for this duopolist, right? Note that I have a function with Q1s in it and a Q2. And recall, right, for our Nash equilibrium, what we want is each player to be maximizing their profits with the strategy of choice of their own, which is the Q1 that firm 1 is choosing here, given the choice made by their opponents, right? All of their opponents. In this case, there's only one opponent. It's firm 2. So where I'm trying to get to here is a Q1 C as a function equal to some function of Q2, right? We'll call it G of Q2 over here, right? There, the optimal choice of quantity for firm 1, given whatever the choice is of their opponent. And then at the same time, right, I can infer from this, because the firms, this is just a generic function, both firms have this true, and some sort of cost function. I can infer that there's a similar situation for firm 2, where all of these are just reversed. A minus 2B Q2 minus B Q1 equal to C prime of Q2, right? Where this is true as long as they have the same cost functions. If they were to have different cost functions, then I should subscript these with the firm number. But so here, essentially, this would imply another function where they are solving for their optimal Q2 given Q1, and our Nash equilibrium is going to be the point where both of those are satisfied simultaneously, right? That would mean that all players are optimizing given the strategy chosen by all of their opponents. So that is where in the next part we will impose a little bit more structure on these equations so that we can actually solve for a closed solution to each firm maximizing their own profits given the quantity choice of their opponent, right? Which is going to be quite simple if we have symmetry, which we will in the next part, and a little bit more complicated when we don't have symmetric conditions for both firms. That being, right, since it is necessary that both firms face the exact same market demand, and this is just an identity that is necessarily true, symmetry is going to depend almost entirely on whether they have the exact same cost functions. All right, we'll be back with that in the next lecture.